Welcome back to part 3. Now we can discuss non-equilibrium statistical mechanics. Okay, in this part 3, we concentrate on several non-equilibrium processes that take place in an equilibrium environment. And of course, the most important, it doesn't look fancy, but the most important non-equilibrium process is the relaxation to equilibrium. So that's what we are going to discuss. And then we consider some operations in an equilibrium environment. Okay, and here the material approach to thermal equilibrium. This is something very, very, very standard. And also fluctuation theorem and the Jaruzelski equality are in these states, these are more or less standard. And here, this is not very standard, but this is a very interesting result. So let me discuss this something called the non-pumping theorem. Okay, so anyway, let us start from the relaxation process in an equilibrium environment. So this is the basic setting. We consider a physical system. It can be a large system where thermodynamics is valid, or it can be something very small like plastic bead trapped by optical tweezer. And here we assume that the system parameters are time independent. Okay, and this is the standard assumption. We assume that physical system takes almost stable states labeled indexed by j that runs from 1 to omega. And by ej, we denote the energy, or more precisely, the free energy of this state j. Okay, and we assume that this system is in touch with the heat bath, which is another large physical system like surrounding water, which is in equilibrium with inverse temperature beta. Okay, and this is again standard for us. The interaction with the bath causes the system to jump from time to time to a state from state to another, okay, in a stochastic manner. So then, if these assumptions are valid, then a very good effective theory for this physical system is a Markov jump. It's a Markov jump process with time-independent transition rates omega. Okay, so as we discussed before, this is more or less faithful descriptions for some physical systems like ionic conductors, trap beads, or classical spin systems and things like that. So this is ionic conductor. This jumps from potential minimum to minimum. And this is classical spin system. Or we consider Brownian motion of a plastic bead trapped by optical tweezer. Okay, and okay, so this kind of description applies to some systems, but this is another viewpoint. We can think of this as a theoretical playground for developing non-equilibrium statistical mechanics. I think this viewpoint is more important. Okay, now we proceed to make our basic assumptions on this transition rates omega. And we assume that this omega satisfies the detail balance condition, or more precisely, the detail balance conditions with respect to the canonical distribution at inverse temperature beta. And this is the condition. And so the ratio between omega kg and omega jk is given by something like the Boltzmann factor for any k and j which are not equal, and omega is non-zero. And actually, this was proved for mechanical model. Yeah, this was proved using some mechanical model and equilibrium statistical mechanics in part 1, page 33. Yes, so of course we made some assumptions like the surrounding water is always in equilibrium, but anyway, in some sense we were able to justify it. We were able to prove this, so we can safely assume this here. Okay, and another assumption, which is again very natural, is that all states are connected through non-zero omega. Okay, this means that if you start from one state, then by making jump according to non-zero omega, you can finally reach any j. You don't have to reach j at once. I mean, if you make jumps many times, then you can reach new j. I mean, this. If you are working on ionic conductor, then this is one configuration. You can think about totally different configuration. Of course, you cannot reach this new configuration at once, but if these particles jump many times, then you get this configuration. Okay, so this is a very natural, I think this is a very natural assumption. And in terms of R, the transition rate matrix, this means that R is irreducible. let me look at this. And this is the definition of irreversibility. And this simply said that you can connect from J to K by using non-vanishing R. So the same condition. So we know that this R is irreducible. Okay. And here's a remark. This condition, the detail balance condition with respect to the canonical distribution, is written like this. Okay. Of course, if you assume this, then this is true. Here, A is some quantity which is symmetric in J and K. Okay. So if this is true, of course, this is true, but the converse is also true. If you have this, you can always write omega in this way. And of course, we don't know anything about A except for that it is symmetric. Okay, but physically speaking, you can say that this character is in some sense characterizes the barrier between J and K. So a typical choice of A, of course, this is not mandatory, but a typical choice, which is sometimes called the Cramer's rule, is to choose A like this, where B characterizes the height of the energy barrier between J and K. Okay, so we don't use this pretty much, but this. We claim that this is a natural choice. Okay, we come back to this when we discuss no pumping theorem. Okay, so anyway, these are two main assumptions: detail balance condition, which can be proved, and this connectivity, okay, or irreducibility. Then we can discuss the approach to thermal equilibrium. Okay, R is related to omega like this, and we know that R is irreducible. Then in part 2, we have this theorem, this very strong theorem. The only assumption of this theorem is that R is irreducible. Then we can show that there is a unique solution for this eigenvalue equation, and this has all positive entries, and this very strong convergence theorem. Wherever you start, the solution of the master equation converges to PS. So now we can make use of this. Good. So yes, so we know from this theorem that there is a unique PS and everybody converges here. And now we have this detail balance condition. Okay, we wrote it this way, but you can bring omega here, and then we have this. And in terms of R, this is written like this. Of course, we divided this by Z to get the canonical distribution. So this is the detail balance condition written in terms of R. No summation. Okay, no summation. This is valid for any K, J which are not equal. Okay. Now, okay, so let's then examine this. So this is basically R operated to P canonical. Okay, so you sum over this. But anyway, we split this into 2. So this is when K equals J. And so the rest is the sum over K, which is not equal to J. Now here, I use this detail balance condition. So then this becomes RKJ, PJ. Now here you have PJ, PJ, and you only have sum over K. So now, again, you can write this as a single sum. K now runs from 1 to omega, including J. So you can write this compactly in this manner. But now you know that if you sum over this first index of R, you get 0. So this is 0. What does this mean? This means that this is 0. And since we know that the solution of this is unique, so we conclude that this PS is P canonical beta. Okay. Actually, this is this statement is more general, as you can see. So if you have a probability distribution which satisfy this condition, then everything is the same, and you see that this probability distribution is nothing but this stationary distribution. Okay, but anyway, in this case, in this particular case of detail balance condition, we see that the stationary distribution is the canonical distribution. And then we can make use of this strong convergence theorem to conclude this. This is, I think, very strong. Okay, very strong. So let PT be the solution of the master equation for this particular R. And then for any initial distribution, you see that the long time limit of PT is the canonical distribution. So this is a minus first law or the zeroth law. I forgot which is which, but of thermodynamics. I mean, so this is a very basic of thermodynamics. If you put anything if you put anything in touch with a huge heat bath, then this is something will reach thermal equilibrium with the same temperature. Okay, it has been proved, of course, within the effective Markov jump process. But this effective description is well established, well justified. So I think this is a very strong and physically meaningful result. And also, if we are dealing with small systems in which we can observe fluctuation in equilibrium, then this result means that the fluctuation is also precisely described by P canonical beta in the long time limit. Okay. We can also talk about very strong H theorem, which we discuss in page 35 of part 2. So which one is? Yes, this one. So here we looked at the relative entropy or the Kullback-Leibler divergence between any probability distribution and the stationary probability distribution. And then we found that this is a monotone non-increasing function of time. And it goes like this. And in this case, this H function or this relative entropy was computed already in, I think, part 2, page 17, and you easily find that it's written like this. And here you have something called the generalized Helmholtz free energy for general probability distribution P. Okay, because this looks like Helmholtz free energy because you have energy here and the entropy here. But probably I said this before, but okay, this is energy, the expectation value of energy. It has physical meaning. But this SP is just an information theoretic quantity, and it's called entropy, but it's not a thermodynamic entropy in general. And you don't know how to measure this in operational manner. Of course, it's mathematically well defined. It's there, but it doesn't mean that this is the thermodynamically meaningful quantity. And so anyway, this is a well-defined quantity whose thermodynamic meaning is not very clear. But anyway, mathematically we have this function. And when P is the canonical distribution, then this F beta becomes nothing but the standard Helmholtz free energy. And so the H theorem says that this decreases, this is non-increasing in T and finally converges to 0. So we can say that this guy is non-increasing and finally converges to F beta. Okay, so this is our theorem. F of PT is non-increasing in T and converges to F beta. I think these are very strong results. Wherever you start, for any initial probability distribution, you know that this converges to canonical distribution, converges to the canonical distribution. And also this convergence is in some sense monotone because this quantity f of pt never increases. It just decreases and converges to f beta. Okay, so this can be proved. And this was very quick, but we made use of all these non-trivial results that we proved in part 2. So I think these are very meaningful results. Now let us discuss a version of fluctuation theorem in the same setting. Now P0, the initial distribution was just arbitrary in this theorem, but now we take it as the canonical distribution, but with different beta than the different temperature than the heat path. Okay, so this is a schematic picture. Here is the system that we consider, and we imagine that it's surrounded by a big heat path. Of course, it's described by this stochastic rule, but we imagine that it's surrounded by this heat path with temperature beta. Okay, so this is our system. So we assume that it's initially in the equilibrium state with different temperature beta prime. This is quite natural. You have something hot and you want to cool it, so you put it in water. This is almost like that. And of course, we know from the previous theorem that this PT is, of course, the solution of the master equation. It finally converges to the canonical distribution with beta, which is the same as the heat path. Okay. Now, in this situation, we want to look at fluctuation theorem. So we go back to part 2, page 47. So this is part 2, page 47, and we formally defined this quantity, which we called entropy production, which is simply the log of the ratio of omega k to j and omega j to k. Okay. Now we do it here. So this is a log of ratio between this and this. But now this is something familiar from this detail balance condition. Okay, so we are taking log of this thing. So then you get this. Yes, you get this. Okay, from detail balance condition, we get this. And this has a clear meaning. First of all, the state of the system jumped from k to j. So this is the initial energy of the system, and then this is the energy after the jump. So this is the energy difference. So this energy difference, of course, by energy conservation, have to go somewhere. And so this is the energy which went from the system to the bath. So this is usually we call it heat. So this is nothing but the heat which went from the system to the bath in this jump. Okay, and now, so this is Q, and then beta Q is nothing but the increase of entropy in the heat path. So this is the entropy. This is nothing but the entropy production in the heat path. It has a clear physical meaning. Okay. Now this was a single jump, so let's look at a path in the time interval 0 tau, which is described like this as before. So these are the list of the states that this gamma visited, and these are the list of time at which jump take place. Okay, and now as before, so yes, we can. Here we have this. This is part 2. Here we had this omega tilde because we wanted to distinguish between omega tilde and omega tilde Dagar. It's time reversal. But here we don't have it. Here in part 3 we don't have anything like time. We don't have any time dependence, so we just omitted this. So this is our entropy production in a single jump, and then this is the total entropy production along the path, which is just the sum over all these quantity for all jumps. Okay, so that's what we do here, and here it's quite simple. So you plug this in here to get this, and this is a very simple sum, and most of terms cancel, and you simply get E in the beginning and E at the end. Okay, so gamma init, gamma final, these are the initial state and the final state in the path, so you can write it in this way. Okay, now you go back to part 2, page 51. Okay, part 2, page 51. Okay, this is and here we discussed rather general fluctuation theorem. The form is very familiar, but we discussed this fluctuation theorem for the probability density for this weird quantity we called psi. And this is the sum over theta, the total entropy production, log p minus log p. And these are the same p, which this is just the initial probability distribution, which is evaluated at the initial state of the path and the final state of the path. And if you look at the probability distribution that this psi is equal to S, then this satisfies this beautiful symmetry. Okay, so now let's go back to our case. So this is psi for our case. And in our case, initial probability distribution P is the canonical distribution. So this is given by this canonical distribution with inverse temperature beta prime. And here the same thing, so you get this. So if you sum over this and this cancel, and what you get is actually here you again get beta prime E gamma final minus E gamma initial, something very similar to this. And finally, you get this combination. Okay, And I should have said this before, but this again has a clear meaning. This is the total heat. Well, I think this is clear. So this represents heat, heat that went from the bath to heat from the system to the bath in mth jump. So you just summed over all these heat. So this is nothing but the heat from the system to the bath through this path gamma throughout the history. Okay, and of course we know that if you consider the probability density that this thing is equal to s, yes, and then this probability density satisfies this very interesting symmetry called the fluctuation theorem. What do we learn from this? Well, first of all, this is rather trivial. This says that, okay, suppose that S is positive, and then here this is positive, this is negative, and here you have something greater than 1. So this means that S wants to be more positive than to be negative. Okay, so this means that this quantity is more likely to be positive. And what does this mean? Well, it means something very simple. Okay, let's look at this again. So beta and beta prime are the inverse temperatures of the bath and the system, and the initial state of the bath of the system. And suppose that initially the system is in hotter temperature. This means that beta prime is smaller than beta. So beta minus beta prime is positive. Okay, and in this case, since this is hot, Q wants to be positive. Okay, because heat flows from hot to cold. So in this case, okay, yeah, and Q is likely to be positive if this is this. So that's the case we discussed. So if the initial temperature of the system is colder than that of the bath, then this is negative, and then Q wants to be negative. So these together implies that heat flows from hot to cold. But of course we knew it. We know this because we know this convergence theorem. This convergence theorem tells you that if the initial temperature of the system is higher than the bath, then it cools down. If it is colder than the bath, then it warms up. So of course we knew it. But anyway, it's confirmed in this precise form. But this is more meaningful if we are considering small system with small temperature difference and small enough time. And in that case, fluctuation will become important. Fluctuation of this quantity will be important. And as I said, this is mainly positive, but there is a chance that these things become negative. That means heat may flow from cold to hot. Okay. But this is weird, but with some small probability this can happen. And this smallness is guaranteed by this equation here. Theta is any dimensionless positive quantity. And then the probability that this becomes negative, of course, this wants to be positive, right? But the probability that this happens to be negative is bounded from above by this, okay? So if theta is very big, like 10 to the something, 10 to the 10th or something, then this is very, very, very small, and this probability can be neglected, just neglected. But if theta is not very small, like 1, 2, 3, this is not very small, so this probability has meaning. Okay, so this is derived in part 1, P25. This is, oops, no. Yeah, this is part 1, P25. And this is just a derivation. It's very simple. Okay, so you just recall this, please. So we can prove this. Okay, and more importantly, for this small system case, the probability density PS exhibits this non-trivial symmetry. So I said that heat mainly flows from hot to cold, but it may flow from cold to hot. Very weird. And these probabilities are precisely related by this symmetry. And of course, we are dealing with effective description in terms of Markov jump processes, but this effective description is partially justified. So I think this symmetry is a meaningful result. And of course, it's meaningful for small systems. Okay, so that's all for this video.